go about 80 down the highway. I can get 30 minutes.
No, you don't. That's illegal.
I go about 80 in a 60 work zone. So I'm like,
Exactly. I'm going to send this to the authorities.
Just make sure they walk.
Hang on again, that way you have to walk.
Yeah.
Okay, so our next test is for another.
it's 28. Let's go. I'm ready to pass it.
All right. So today we'll talk a little bit more about the Gibbs free energy, internal energy, and some other such things. And we'll kind of see where we end when we finish all this stuff as to whether or not we talk a little bit about the future sections, right? But after this, we'll then start talking about equilibria, specifically phase equilibria and things like that, thermodynamics that determines phase boundaries and other such things. And then we'll talk about equilibrium mixtures and such, and chemical equilibrium is part of that, as well as then talking about electrochemistry. I'm trying to remember the rest of the semester how it plays out here. I guess I can look at the schedule. Yeah, phase equilibria, mixtures of stuff. Spent a long time on mixtures. Yeah, and then electrochemistry. Yep. So that's kind of the layout for the rest of the semester. Okay. Again, I'll just make a note, right, that for exam 2, I very much review your exam 1, because exam 2 will have not every question, but will have at least a couple questions. They'll probably be very similar to exam 1, except then you got to calculate entropy or Gibbs free energy or something else like that. Right? Like, so the same type of things that are in exam 1 can easily pop up in exam 2 because there's kind of the most overlap between those material. Right? Exam 3 will be definitely more unique compared to 1 and 2, because by the time we get to exam 3, we'll no longer talk about compressions and expansions of gases, right? And so that will definitely be different. But exam 2, we're still talking about compressing gases, but then calculating entropy changes for those things, Gibbs free energy changes, and so on. Okay. Right. Last time we had talked about Gibbs free energy changes under non-constant temperature or pressure conditions, right? If one was something constant, but then the other one changed, right? Constant temperature, but changing pressure, constant pressure, changing temperature, right? Okay. So yeah. So questions we'll have. Let me open up the chat window thing here. Yeah, questions that people have before we get going about anything. Whoever. The what?
The key to exam 1.
Yes. So it's posted there. I think I included the link to it in the announcement, but also it's here. Just let me real quick. If you go to the files, maybe I could create like a module for this, but if you go to files and then exams folder, there's exam 1 solutions. Click on that and let me just double check. Oh, nope, that's not right. Oops. Well, maybe not. Maybe from a previous exam. Where did that file go? Did I put in supplemental notes here? All right. Well, I thought I had uploaded it. Should have been uploaded. I think I accidentally uploaded the wrong exam 1 solution. So.
I can see it. In that exam folder.
Yeah. Yeah, but if you click on exam one solutions, it's just a document that has like some answers, and they're answers to an exam that had total 5 questions, and you guys had total 4 questions, I think, if I recall.
Don't study that.
So yeah, no, that's a completely different problem, right? Yeah, so I think I just accidentally uploaded the wrong solution. So thank you for saying something about that. I will fix that after class. So that's right. I did add something to the supplemental notes with examples of thermodynamic changes, where kind of what we did at the end of class last time, and maybe we'll continue this class, right, where I have a bunch of just questions of different example problems for thermodynamic changes, and not working out the numerical values, but just discussing, like, thinking about what's changing, what's being constant, what does that mean in terms of what equations are relevant and not relevant, and things of that nature, okay? And kind of going through that. So, it's just more practice for those type of things, right? I mean, in those supplemental notes folder, right, there is, again, the notes from a previous faculty member that it's broken up into topics, which topic numbers are still in the back of the syllabus, right? Kind of, summarize stuff that's in the book and stuff we've talked about, as well as has example problems with answers to them. And then some other different notes that I've put up there about kind of thermodynamic changes, stuff about partial derivatives, phase diagrams as we start talking about them now. So just extra kind of random notes for people to look over. But yeah. So the exam solutions should be there, but I obviously uploaded the wrong solution. So I will upload the correct ones, which have like my stuff worked out on them and everything else like that. So yeah, those will be up there. Other questions people have? All right. As a reminder, videos for lectures have been posted last week. Are available online for those to view and watch. As always, I recommend you watching those videos, looking over the book for class. But yeah. So, okay, last time we didn't show this, but so ignore that from last time, because we didn't end up doing it last time. But right, using the first law of thermodynamics, the definition of entropy, and then definition of reversible work, okay? And the fact that U is a state function and things like that, you can show that a change in internal energy is related with some temperature times a change in entropy minus pressure times some change in volume. And this is known as the fundamental equation. Honestly, I have no idea why it's called the fundamental equation. I assume because it includes, kind of fundamental properties of your system, the internal energy, its entropy, right? Those are defined values, right, that have absolute zero things, right? It has an entropy, has an internal energy, right? Has a temperature, has pressure, has a volume, okay? So those are all kind of fundamental properties of your material, right? And not necessarily talking about heat or work, which are talking about transfer of energy, right, from system and surroundings, okay? This equation relates how a change in internal energy is accompanied by or caused by changes in entropy or volume through this equation here, okay? All right, and using kind of that equation, we could think, right, if we look at this equation, we say, okay, if this is sort of a total differential, right, of internal energy, right, a multivariable total differential is the partial derivatives with respect to each of the individual variables times like the, dx, dy, dz, or whatever, right? So if I look at this, right, this is kind of saying, well, I could think of internal energy here as a function of entropy and volume, right? Because it has kind of this form, right, where du equals del u del s ds plus del u del v dv, right, which is, again, this is a total differential, okay, of some multivariable function, okay? Right? So this is just kind of, again, a mathematical technique saying, hey, if I got this multivariable function, if I think of this function as a function of entropy and volume, then this is what that total differential, right, what the change in du is related to in terms of changes in ds and dv. Then we compare that with the fundamental equation on the previous slide, right, which is du equals tds minus p dv. And we get, oh, yes, I don't have that slide here, right, but we get the fact that du ds is equal to t, and du dv is equal to minus p, right? So it's a relationship, equation and that equation, right? That del u del s is equal to temperature, del u del v is minus pressure, okay? And then using the fact that u is a state function, means that it as an exact differential, right? If we recall, we talked about this before, right? An exact differential essentially means that I can take the derivative of u with respect to s, and then derivative of u with respect to volume, and that's the exact same thing as taking the derivative of u with respect to volume, and then the derivative of u with respect to s, right? So the order of my derivatives does not matter, okay, for a state function, okay? And so if I take the derivative of u with respect to volume and entropy, or entropy then volume, you will get this relationship right here. I'm missing the minus sign because there should be a minus sign here. Minus PDS. TDV. Okay, so it's this relationship here, though this is the reciprocal. I don't know why it's written in reciprocal form, but that's fine. So you can get this relationship, which is some of the Maxwell relations, okay? Okay, now these relationships, okay, so for example, that bottom one, the derivative of the volume with respect to temperature under constant pressure equals negative the derivative of the entropy with respect to pressure under constant temperature, right? These relationships are all 100% true, okay? For some system, the changes in volume with respect to temperature under constant pressure is the exact same type of change as the entropy with respect to pressure under constant temperature, okay? These changes are identical to each other, okay? Right? But the usefulness of these Maxwell relationships, which again, we get these Maxwell relations from the fact that our internal energy, our enthalpy, our Gibbs free energy, our Helmholtz free energy, these things are all state functions. Because they are state functions, they have exact differentials, and so I can go through and kind of derive these things from the properties of those things, right? The internal energy, entropy, Gibbs free energy, etc., right? And again, so all of these relationships are 100% true and are valid for any system. There's no approximations being made here, okay? Not assuming ideal gases, not assuming any phases, not assuming constant anything, okay? These derivative relationships are always true, okay? But again, and as kind of the top of the slide is indicating, right, none of these things are intuitive, right? And so what's the point of all of this, right? Well, let's say I want to know, right, for my system, how the entropy changes with volume as holding temperature constant, okay? If I want to know that relationship, how is that entropy changing with volume under constant temperature, right? I can always measure in my system how pressure changes with temperature under constant volume. And that gives me the exact same slope, right? That exact same relationship, right? So I could measure these more easily measurable quantities, say on the left side of these equal signs, to gain some insight as to what's going on the right side. Okay? So that's kind of the importance of these Maxwell relationships that can be used to help understand things that might not be easily understood, might not be easily measured. Okay? Questions about fundamental equation or Maxwell relations. You do not need to memorize these whatsoever, just so you know. But, you know, we have a question here. So if I have some state function f, where I can write its total differential, df is a dx plus dy, which of the following choices is the resulting Maxwell relation from this differential f? Anyone have any thoughts? Some B's here. So B is true, that df dx when it comes to y is equal to a, but that isn't necessarily the resulting Maxwell relation, right? So the Maxwell relations, right, come from, again, the idea that d dx of df dy is equal to d dy of df dx, which, if you go back to the slide, you see that df dy is equal to b, and df dx is equal to a. This is db dx equals dA dy. And that is your resulting Maxwell relation for this function, right, which is C here. Yep. All right. Again, that's how, like, these equations are obtained, is they start with, like, this fundamental equation here, right, and say, okay, u is a state function, has an exact differential, so that means the derivative of t with respect to pressure has to equal the derivative of, or sorry, derivative of t with respect to volume has to equal the derivative of pressure with respect to entropy, with this minus sign in here, right? There's a negative, but right, and so yeah, so we get those relationships, those Maxwell relations. So again, using the fundamental equation, the definitions of Gibbs and enthalpy, okay, we can show that you get this relationship: dg equals vdp minus sdt. Oh, wait, no, so maybe we didn't do the Gibbs free energy as a function of, yeah, that's, did we talk about this last time? I don't think so, right? No. Okay, so actually last time we didn't get to this, yeah. Right, and so, again, I can write my Gibbs free energy as volume dp minus sdt, right, instead of, like, dh minus tds, or, you know, minus sdt or something like that, right? So this Gibbs can be thought of as a function of pressure and temperature, Okay. And again, using that, let's see, pressure, what's it again? Pressure, temperature, so. That one. All right, I'm just kind of looking at my things here. And I think actually I just have one of these Maxwell relationships written wrong. Yeah. Let's see, because yeah, V dt and S dt. Yeah, so this one is from the Gibbs free energy. I think I just didn't write the one. I might have just not written the one from internal energy U. That's it. Okay. So I'm missing a Maxwell's relationship here. Like this doesn't make sense. But anyways, so using this, okay, right? Because the Maxwell relationship from this equation here is saying dV dt equals minus ds dp. Okay. That's what the Maxwell relationship is from this. So the differential, okay, take this derivative of this with respect to that, and the derivative of this with respect to that. Get the Maxwell relationship. So what you can use, get this form of G as a function of temperature and pressure, I can look at what is the change in temperature dependence of Gibbs free energy and constant pressure. And you get this relationship here, which is not necessarily very nice and neat here, but minus the enthalpy divided by temperature squared equals the derivative of the Gibbs free energy divided by temperature with respect to temperature under constant pressure. Okay. This can also be written in this form, okay, that the derivative of the Gibbs free energy divided by temperature with respect to 1 over the temperature is equal to the enthalpy, okay, which this form kind of just gives you the idea that, hey, if I plotted G divided by T and 1 divided by T, okay, that the slope of that will give me the enthalpy in my system, right, or the enthalpy change, okay. Right. And this is the Gibbs-Helmholtz equation. Okay. We'll talk about this more. We can talk about phase changes and such, and looking at some of these things with phase changes. But for now, just kind of introducing the fact that if you take this equation here, okay, and you plug in for what entropy is and things of that nature, okay, in terms of enthalpy and such, you can get to this form. Okay. And again, this is the Gibbs-Helmholtz equation. Okay. It's not something you need to memorize. It's something we will use eventually. Okay. And then if I look at the pressure dependence of Gibbs free energy on the constant temperature, okay, again, I start with that equation. Temperature's constant, I just get dG equals V dP. Okay. For solids and liquids, that volume is basically a constant. The change in Gibbs free energy, the change in pressure is just V times delta P, right? Really simple. Gas, that volume is equal to nRT divided by pressure. So you integrate that, and the change in Gibbs free energy is nRT ln P final over P initial. And so that those relationships, right, for solids, liquids, just volume times the change in pressure. Or for gas, nRT ln P final over P initial, right? It's how Gibbs free energy changes under constant temperature with a changing pressure. Okay. Right. And if you were to use this equation to calculate delta G for an isothermal expansion of an ideal gas, you'd get the same answer if you calculated delta H and then did delta S and did delta H minus T delta S. You'll actually get the exact same. Okay. Based off of basically, yeah, delta H is it is CP delta T. Well, actually, no. Delta H is 0 for an ideal gas, an isothermal expansion. then delta S is related with, you know, ln of nr ln v final over v initial, multiply that by T, multiply by a minus sign, and then swap out pressures for volumes. Using your ideal gas relationships, you'll get this equation. So yeah. So you can derive this equation from this relationship here, or from isothermal ideal gas. At least you can show this same thing. Okay? Using delta G equals delta H minus T delta X. Okay? Again, the Gibbs-Helmholtz equation, we don't really have a nice, useful form of integrating this crap out to get some equation to calculate delta G for some temperature change. And we're not going to bother doing that for like an ideal gas, but again, this will be used later on when we talk about some stuff with phase changes and things of that nature. Okay? So questions about these Maxwell relationships, Gibbs free energy changes with respect to pressure or with respect to temperature. Okay. All right, and one final thing that we're going to talk about, just introduce here, we'll talk plenty about for a long time, is how these quantities change with the change in number of moles, right? We basically, for the most part, focused on constant number of moles, okay? But the question is, right, is how does the Gibbs free energy change with the change in number of moles, the Helmholtz, enthalpy, internal energy, right? And all of those things are related with the chemical potential. So mu is called the chemical potential. Out of curiosity, how many people have heard of the chemical potential before? Sort of, really, at least outside of this class. Maybe you watched the videos or read the book, right? So you heard of it there, but outside of this class, not really, right? Right. So chemical potential, and it was similar for me actually. Even in most of my undergrad and even graduate studies, didn't really talk much about chemical potential. Okay, but chemical potential is a very useful quantity, a very telling quantity, and controls a lot of things. So when we talk about phase equilibria, it will all have to do with chemical potentials, and why certain phases are in equilibrium at certain temperatures and pressures is because of their chemical potentials and how the chemical potentials change with temperature and pressure and such. Why colligative properties are related with, again, chemical potentials being equal to each other in certain phases, which is mixtures of things. Okay? Chemical equilibrium is all about having the chemical potentials between your reactants and products equal each other. That is when you reach chemical equilibria. Okay. Right. And then even in physics, if you talk about Fermi levels and other things, transfer of electrons between two semiconductors or other things like that, it's all about equating the chemical potentials between two materials. So this chemical potential plays a very big role in chemistry and is often kind of just behind the scenes and things. Okay? And so we're as we go about talking about changes, mixtures of systems, and other such things, we'll be shedding a lot more light on the chemical potential, okay, and its importance and relevance, and essentially how using the chemical potential and our understanding of it, we can derive a lot of relationships that we've seen in chemistry. Okay, so we'll see a lot more of this in future days. Okay, but again, now often we'll relate the chemical potential to a change in Gibbs free energy, expect to change in number of mole, because often we're dealing with constant temperature pressure systems. Okay, so that's how of the chemical potential, right? But if you're under constant like entropy or pressure, constant entropy, constant volume, constant temperature, constant volume, right? Then the chemical potential can be related with changes in internal energy or Helmholtz free energy or enthalpy, right? But again, in chemistry, we often are just focused on constant temperature pressure systems, right? And so we're going to basically talk about the chemical potential being related with the change in Gibbs free energy with respect to the change in number of moles. Okay. All right. So yeah. So, right, and so the missing variable then, right, from this, say, if I want to do the fundamental equation, if I want to think of the internal energy, right, as not just a function of entropy and volume, but also number of moles, right, what is this missing thing in front of dN going to be? Right? To be A, right? The chemical potential, right? Because this is, right, if I think of U as a function of entropy, volume, and number of moles, right, this quantity here has to be du ds, to equal temperature. This quantity here has to be du dv, which equals minus P. And this quantity here, right, has to be du dn, which, right, as talked about in this last slide, du dn, right, equals the chemical potential. Okay? So the missing quantity here is this chemical potential, right? And so all of these equations, these differentials for internal energy, enthalpy, Gibbs free energy, right, that we've been talking about, right, all of them we can just add on mu dn if we want to start talking about how they change with the number of moles of some compound. Okay. All right. Just a reminder and review of some concepts talked about previously, right? So the following statements is or are always true for spontaneous process. Right? Only three. A lot of people saying, right? Delta S of the universe is less than 0. It's the exact opposite, right? Delta S of the universe is greater than 0 for spontaneous processes. Okay? Delta G less than 0 is not always true, right, for spontaneous process. It's only true for spontaneous process if the temperature and pressure are being held constant. Okay? But 3 here, delta A, the change in Helmholtz free energy being less than 0, is going to tell me if something spontaneous if my system's under constant temperature and volume conditions. Okay? So 3 here is true, but the other 2 are not always true or true at all. So yeah, so it'd be just 3 here, so C. All right. So using this relationship, delta G equals V delta P at constant temperature. When evaluating the expression for gases, you can always assume the gas behaves ideally. True, false on these. This is actually going to be C, none of these. It's sort of a trick question. Right, that equation, delta G equals V delta P, only works for liquids and solids where the volume is independent of pressure. For gases, right, volume definitely depends on pressure, and so this equation does not hold. And so it doesn't matter if you assume an ideal or real gas, you shouldn't be using this equation in the first place. Right? So it's kind of a little trick question, right? That equation is not used for gases at all, because to get to delta G equals V delta P, you had to assume volume is independent of pressure. And for real or ideal gas, that is a very, 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 very bad assumption. We see here like none of these. Not false, not true. Don't have to. All right. So calculate the change in molar Gibbs energy of water as a liquid versus water as a vapor, and considering it as an ideal gas, if I change the pressure from 1 bar to 2 bars isothermally at 298 Kelvin. And I guess technically, huh? I mean, I guess, yeah, I was going to say here, I'd need to potentially include the density of water, right, is 1 gram per centimeter cube, I guess. Yeah. Toss that in. Well, so you're looking for the molar Gibbs energy. So it's going to be delta G divided by N, right? Which is then related with the molar volume, right? Volume divided by N, and then the molar volume is related with the density. All right. So, let's do the gas first. 1 bar to 2 bar, right? 290 coming. Okay. Right. So we're going P initial equals 1 bar, P final is 2 bar, T equals 298 Kelvin, right? So for an ideal gas, a change in Gibbs free energy is equal to nRT ln P final over P initial. Okay. Right, and I'm looking for the molar Gibbs free energy, so I got to divide both sides by n here, right? So the delta G M is equal to RT ln of that P final over P initial. Okay. So just plugging in things 8.314, 298 Kelvin, ln of 2, right?
Professor, yes.
Huh?
On your last slide, you had that question about can you use that equation, like if you can assume if it's an ideal gas or not. I didn't really understand that if we're using this equation now.
Yeah, so this is for part B, for an ideal gas. And for an ideal gas, so that slide, let me go back to the slide real quick. Right, so for this slide, it was sort of a trick question because the idea is this equation here assumes volume is constant with pressure, which is only true for solids and liquids and not gases. So you would never use this relationship to change in Gibbs free energy and to change in pressure for a gas. You'd only use it for solid and liquid. And for a gas, if you assume it's an ideal gas, which is what's stated in this problem, then you would use the relationship written out here, delta G equals nRT ln P final over P initial. Okay.
Okay, that makes a lot more sense. I got the equations confused.
Yeah. So I did part B first before part A. So yeah, this is like part B with assuming for an ideal gas. And we'll do part A next. Okay.
Thank you.
Yep. All right. Other questions? Sorry for those who are in class. I forgot I froze the screen. But yeah. And I'll flip back to the slides to get the numbers. Okay. But the other part, right? If I look at treating this part A, right, a liquid, right? That delta G is equal to V delta P. Okay. I'm looking for the molar Gibbs free energy, so divide both these sides by the number of moles. Okay. So this is delta G sub M equals V sub M delta P. Okay. Now the molar volume, okay, is related with liters per mole, right? So if I end up dividing by the density, I'm multiplying by the molar mass, or molecular weight, okay? This will give me liters per mole or volume per mole, okay? Molar mass is grams per mole, and then density is grams per volume. So like your units here, this is grams per mole. This is grams per volume, okay? So your units will work out to give you volumes per mole. Okay, so the molar volume of a liquid or solid is just the molecular weight divided by the density, okay? And so this is roughly 18 grams per mole over 1, so grams per mole over 1 grams per centimeter cubed, okay? This is basically 18 is the molar volume of the liquid water here, okay, given its density. Now this is in centimeters cubed, okay, per mole, right? So I need to keep that in mind, right? So when I do delta G, okay, I'm going to convert this, what should I convert it to? Probably liters, okay? So to convert this to liters, I have to divide it by 1,000, so 0.18 liters per mole. And then if I write this, and then I have the pressure is 2 minus 1 bar, right? So this is 0.018 liters bar per mole. Okay. And then for converting from liters bar to joules, I think you just multiply by 100. So if I times all of this by 100, that converts from liters bar to joule. Okay. And so delta G here. So for this, the answer is 1.8 joules per mole. Okay. What delta G is for the liquid. Okay. And let me go back to the slide. So all this is also written in the slide here. But I wanted to go back for the gas, right? Ends up being 1,717 joules per mole, right? So a lot bigger change in the molar Gibbs free energy for a gas than it is for a liquid, right? And you should expect that just because the volume of that gas, right, changes a lot more drastically, right, than it does for, say, a liquid or a solid. Okay.
I had a question real quick. Going back on the last question. So when we're solving for the Gibbs free energy, it's pressure final over pressure initial. When it's for entropy, it is pressure initial over pressure final.
Yeah. So for entropy, we got that. So this is assuming a constant temperature process, right? So under constant temperature, okay, so I guess for an ideal gas under constant pressure, V final over V initial equals P initial over P final. Okay. So entropy, when we first derived it for a constant temperature system, was NR ln V final over V initial. Let's see here. Is there a minus sign in this definition? Let's see. Work is negative of that divided by T. Heat is negative of that. So that's it. No. So yeah, positive. So that's good. Okay. If I plug in for the pressures, right, this is NR ln P initial over P final. And then if I just flip the pressures, it brings the negative sign out. So that's negative NR ln P final over P initial. And then delta G is minus delta H minus T delta S. For an isothermal process of an ideal gas, this is equal to 0. And so I just multiply this by negative T, and I get nRT ln P final over P initial. Okay. So that's
for that same equation, we could just use like V initial over V final if we were given volumes.
Yeah, if you were given the volumes, you could use V initial or V final, right? Because again, for an ideal gas, for isothermal, right, isothermal change of an ideal gas, right, you always have this relationship between volumes and pressures, right? And that's you just derive that from the ideal gas law, PV equals nRT, okay? Right? Because you have P initial, V initial equals P final, V final, right? Because nRT is just a constant. So the product of pressure and volume has to equal each other at all times when you're changing a gas isothermally, right? Assuming constant number of moles. And so, yeah, so the ratio of volumes and pressures always hold true for an isothermal process as such. And so, yeah, if you were given a problem, let's say you were calculating delta G, where pressure is changing under constant temperature, but you weren't told pressures, you were told volumes, you could, instead of doing P final over P initial here, you could just do V initial over V final, or negative V final over V initial, right? Again, right, there's more space here, so I'll go here, right? Negative ln of x equals ln of 1 over x, right? Or negative ln of x over y equals ln y over x, right? Just property of the logarithm functions and things like that, that you bring up the whatever's in front of the natural log into the power of these things, right? Because this is ln of x to the minus 1, right? X to the negative 1 power is 1 over x, right? So that's how that is working. Okay. Just a reminder for those But yeah. So, other questions? For a liquid or solid, yes. Yeah. For a gas, I mean, technically for a gas, yes, but the density of a gas is not really constant. So it's not really, I mean, we often don't talk about density of gases. We just talk about the volume or the molar volume of a gas, right away. But technically, if you're given the density of a gas, then yeah, you could do that, right? Yeah, so that relationship between molar volume and density is always true, okay? This guy up here, right? This is always true for any phase or whatever, okay? The relationship between the molar volume and the density is just given by the molecular weight. They're inversely related, okay? Right, because the more dense something is, right, saying the more amount of stuff you have per volume, okay? So, right, and so, what's that, right, the density is saying, like, how many grams take up 1 liter of space, right? While the molar volume is telling us how many liters, like 1 mole takes up, right, 1 gram. So they're kind of inverse, what they're describing is inversely related to each other, right? The more mass takes up, more mass you can fill into 1 liter means the more space you need for 1 gram or something like that, right? All right. Okay. Other questions about this problem? Right. Here, what I use is the density. Oh, okay. I did molar. Okay. Yeah. So I used the molecular weight of 18.02. So that's how I got like. Oh, but yeah. Oh, but then I used atmosphere. Okay, that was my. I was like, why is this slightly different? Because I used atmosphere for some unknown reason here. When the pressure is given in bars, right? Pressure is given in bars, not atmospheres. Yeah. So that I can fix that, but yeah. So numbers basically kind of the same. I just made a mistake here and put atmospheres instead of bars, and so that messed up my conversion. All right. So any other questions about that example? All right, so if I have 0.2 moles of an ideal gas expanded isothermally against a constant external pressure of 0.85 atmospheres, we do this. Oh, we did this problem, right? Maximum amount of work on the maximum amount of work. Do we do this, or maybe not because it's an isothermal? Yeah, no, we did this because we got. Yep, no, we I don't remember. We did this. Yeah, last time. That's right. So people want to go over this kind of question again. I'm happy to talk about it, but we did kind of talk about it last time, right? And so the idea is I have an isothermal expansion, okay, and it's what is the maximum work, right, for expansion and non-expansion work, okay? That's related with delta G and delta A, okay? Which is related with enthalpy, internal energy, and entropy, right? For an isothermal process of an ideal gas, right? Enthalpy and internal energy are 0, okay? And so you just got to worry about entropy. For entropy, we can assume instead of it being a constant external pressure expansion, we can pretend we did the exact same expansion reversibly and isothermally calculate the entropy, right? To get that the entropy change is 2.2 joules per Kelvin, and then just use the fact, again, delta H and delta U are 0, so delta G and delta A are just minus T delta S, which gives us 715 joules. And in this problem, I calculated what the work was for the irreversible process just to show that it is less than the maximum expansion work. So what I'm going to do now is well, I guess, are there questions about what we've talked about today? I know I already went away from those slides, but I'm happy to go back. I apologize for not waiting to ask this first, but are there further questions about these Maxwell relations, fundamental equations, right? Changes in Gibbs free energy with respect to temperature or pressure. Okay. Again, oh, now I forget the name of the equation now. But minus h divided by t squared equaling dg over t dt. That relationship, which I forget the name of it now off the top of my head, right? Gibbs-Helmholtz, thank you. So the Gibbs-Helmholtz equation, right? That equation we'll use later, but I have nothing right now that we can really talk about and use for at the moment. Okay, but again, it will pop up. We talk more about phase changes and such. Okay. All right. So, any questions about any of that stuff? Any of those examples? Yeah.
So there's like one Maxwell relation for one for 50.
One for entropy. Yeah. So I think there's 4 or 5 Maxwell relationships.
4 or 5.
Turn them on.
Okay.
Yeah. Well, I don't know. There should be 5. Now I don't know if there's. I can't think off the top of my head, but I'm not going to guarantee there's just 5. I mean, in terms of things we've talked about in this class, there's up to 5 Maxwell relationships that we could show or derive. You do not need to memorize those Maxwell relationships whatsoever. I guess in full disclosure, right, that multiple choice question of what are the Maxwell relationships for, this, function df equals a dx plus b dy, okay? That type of a question appears on the ACS final. And so that's why I make sure to kind of talk about it and express it and things like that, because it does appear on the final. But there isn't really any kind of types of questions we do on homework or here in class that we can really ask using these Maxwell relationships besides, that type of a question. The applications of those relationships are often a lot more kind of tricky and complicated and nuanced depending on the problem and things of that nature. So, but yeah, so the point of kind of the Maxwell relationships is just kind of discuss the idea that they do exist, that there are these equations that are valid and always correct, but are not physically intuitive and can be used to help try to solve problems that may not otherwise be solved. Other questions? I'm trying to think what we've done here. No, we didn't do this. So let's talk about this one, right? So how would I calculate work, heat, internal energy, enthalpy, Gibbs free energy, entropy, Helmholtz free energy, and even the entropy of the surroundings? I think I added that one in after class. The freezing of 1 mole of water at -20 degrees Celsius, given the enthalpy of fusion is 129 kilojoules per mole. Okay. All right. And so kind of the first questions, again, we can ask ourselves, right, what is changing in this problem and what is being held constant, okay? So what things are being held constant for this problem in our system? Temperature, pressure, Right, so temperature in the system is constant, pressure is constant.
How do we know the pressure is constant?
I guess it's not explicitly
It
written,
doesn't say.
but any chemical reaction or phase change, pressure is constant. If this problem were given like on an exam or something like that, I'd more explicitly say like, this is happening at, standard temperature pressure conditions or something like, something to indicate the pressure in your lab is 1 bar, right? Right, which then tells you its normal freezing point is 0 degrees Celsius and blah, 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 blah. But yeah, but any chemical reaction or phase change, it's assumed you're under constant pressure conditions. Okay. Here, the temperature is being held constant at 20 degrees Celsius. Okay. So, temperature is constant, pressure is constant. Okay. What about volume? The number of, so if you think about the number of molecules, yes. But often when we think of the number of moles, we think of the number of moles of a specific compound, species, in a specific phase. So in which case, in this problem, the number of moles is thought of as changing because the moles of moles of, what are we starting with? Liquid, right? The moles of liquid goes from 1 mole to 0 by the time this problem's done, right? And the moles of a solid goes from 0 to 1, right? So you can think of this as a chemical reaction, right? The number of moles of your reactants and number of moles of your products change over the course of this problem, right? And so while the total amount of stuff in your system is constant, right? The identity of what those stuff are in, right? It's chemical makeup and phase is changing, right? So in this case, we'd say the number of moles are changing, N is changing, okay? And then volume as well is going to technically change here. Now, not by much, but technically the volume of a liquid is different from the volume of the solid, so it will change very slightly.
So there was also a question like this homework. I was this question. What is the starting temperature of the water?
No, it's starting at negative 20 degrees Celsius. So it's basically the idea is you have a glass of water, you put it in the system, in your system surroundings, and somehow you got it to negative 20 degrees Celsius. Yeah, before it froze. So you're assuming you're right, because you're basically kind of assuming that the water itself, right, is at that negative 20 degrees Celsius and it's freezing at that temperature. Okay? Now I understand, like if you were to put it some water in the freezer, right, that water will slowly freeze as it cools down to 0 degrees Celsius and then starts freezing at 0 degrees Celsius and then cools down some more.
On the homework, I just assumed it was at transition.
So I mean, the idea for these problems is sort of you like flash freeze the water to negative 20 degrees Celsius, or something like that, right? It's in this unstable, metastable state, right? And then you let it do whatever it's going to do, right? That's sort of the idea. Yeah, I guess, placing a glass of water in a freezer, you technically would have the energy change of cooling it down to 0 degrees Celsius, then the phase transition stuff going on at 0 degrees Celsius, and then the cooling of that solid down to negative 20 degrees Celsius. It'd be kind of, it would happen in a more reversible path than kind of what's kind of being pitched from these problems. So sorry if that wasn't clear on the homework, but yeah, the idea is the water is at negative 20 degrees Celsius itself, including the surroundings. The water and the surroundings are all at negative 20 degrees Celsius, right? So maybe you prepared this negative 20 degrees Celsius water, right, at some very, very extreme low pressure. Actually, I don't know what the triple point is of water to know if that's even possible. Pretend it is that, you have some extreme low pressure, right? And then you just get it at negative 20 degrees Celsius, and then you crank up the pressure so that, it's that 1 bar, negative 20 degrees Celsius or something like that, right? Yeah. That's a good question. Yeah, and then I'll say if ever on homeworks, especially on exams, if you're ever confused about something like that, like, hey, does this problem mean this is happening to that? Ask me. You know, I'm more than happy to help explain like what's happening in the problem. Okay, if you're confused about it, you know, for the most part, right? Trying to think of an example of like where I wouldn't necessarily explain if you know somehow explaining it is telling you the answer, then I guess I wouldn't. But like, you know, in this problem, right, you're saying, well, does that mean that, you know, the water itself is cooling down and then freezing and then cooling as a solid? Or does it mean like my water's already at negative 20 degrees Celsius and then it freezes? Right? More than happy to answer that question, right, on the exam. Okay. So again, I'm always happy to try to clarify things as best I can without giving you the answers on exams. So always feel free to ask questions during the exams. Yeah, right. So number of moles changing, right? Volume's changing, but pressure and temperature of our system being held constant. Okay. I'm gonna like somehow remove. You know, actually, let me just not do that. Let's just do this. Let's write these out by hand, right? Instead, I don't want to necessarily just give away all the things, right? So let's write this out at hand, right? We know, right? So variables like changing, things that are varying are moles and volume, right? Constant is pressure, temperature, okay, right? And so then the question is how do we calculate different things, right? How would we get work, for example, for this, right? And P external, right, is also being held constant, right? So for this problem, how would I get work? Right, minus P external, delta V, right? Now in this case, I'm going from liquid to solid, so that change in volume is almost negligible. So this is going to be effectively 0, right, for this problem. But technically, it's minus P external delta V, right? And there is a difference in the volume of a liquid and a solid, so you could technically, given the difference in densities between those substances, calculate the difference in volumes and get a value for work. You'll get it to be a very, very small number. All right, how would I get, you know, what equations would I potentially use for delta U? Or delta H, or anything you want. Right, delta U, I could use Q plus W, exactly, right? What about Q? What's Q related with? Not quite. So in this case, delta U isn't necessarily 0, so it's not going to be minus W. But if I have
Under
something
constant pressure, it would be enthalpy.
Yeah, so because my system pressure is constant and it's the same as the external pressure, right? 1 bar, right? So again, for reactions and phase changes, basically, you know, unless you're talking about like in a bomb calorimeter, which is a constant volume system instead of constant pressure, right? Our system is set up to where enthalpy and heat are going to be the same thing, which is again why we care so much about enthalpy for chemical reactions, because it tells us about the heat transfer for a chemical reaction. Okay. Right. And how would I get delta H for some phase change, right? Given, right, we're given the fact that delta H fusion is equal to some number, right? 121 or something like that. I don't know what it was, right? But some number, right? We just, yeah, number of moles times the enthalpy change for fusion. Now, fusion is solid to liquid. Here we're going from liquid to solid, so it'd be a negative of this, right? So it's negative because this, again, so here this is going solid to liquid. In the problem, right? We're going from a liquid to a solid. So I'm flipping the direction, right? I'm flipping my chemical reaction, which changes the sign of the enthalpy change for that chemical reaction, right? So I would need negative N delta H fusion, right? To get delta H, which will also give me Q, which I can then use to get delta U this way, right? Now, technically, for phase change or chemical reaction, what other relationship do we have between delta H and delta U? Yeah, RT delta NG, right? In this case, there's no changes in gas, so we basically say this is essentially zero, right? Delta H or delta U are zero, equal, right? Which is what we get from this relationship, assuming, right, the work here is effectively zero, right? Which again, the volume change between the liquid and the solid is very, very, very small, okay? So your net work here should effectively be zero, in which case delta U and delta H are effectively equal to each other for this problem. Okay? Right, so those guys, what about entropy?
The N delta H over the temperature transitions at.
Yeah, so one formula for entropy we'll need is minus, right, N, right, it's going to be related with Q, right, reversible over T minus N delta H fusion divided by temperature fusion, right? Now this, but we'll need more. We'll also need entropy change for a CP ln T final over T initial. Right now we're not given all the information needed to solve it, right? But I need something like this as well, okay? Because again, for this process, for my entropy, I'm going to have to create a reversible pathway that connects my initial and final states, because this is an irreversible process, right? And for that reversible pathway, right, I'm going to like heat my liquid, right, from 0 degrees Celsius, or from minus 20 degrees Celsius to 0 degrees Celsius. I then convert that liquid to a solid at 0 degrees Celsius, right? And then I'll cool my solid, right, from 0 degrees Celsius to minus 20 degrees Celsius, right, to get that, you know, freezing of my liquid to solid at minus 20 degrees Celsius, okay? Right? And so I'll need this relationship to get the entropy change here, right? And I'll need this relationship to get the entropy change of the heating and cooling of my liquids and solids, okay? Right, assuming, right, some, yeah, I mean, you'd have to be given CP. You're not given enough information in this problem. Yeah, when I wrote these problems, I didn't think hard about what all you need to know to solve it, because I didn't want to bother solving these things numerically. But yeah, oh yeah, yeah. Assuming constant CP, thank you. Yeah. Well, so the CP of the liquid and the solid will definitely not be the same, so they won't quite cancel. But yeah, so they are different. They're not as different as like liquid to gas or solid to a gas, but the heat capacity of a liquid and solid are going to be slightly different, right? Because basically, you know, it takes more energy to heat up to change the temperature of a liquid than it does of a solid, because the molecules are more able to move around each other and things like that. So that greater degree of motion means you got to put in more energy to, on average, increase their kinetic energy. So yeah, so CPs of solids and liquids won't quite equal each other. So those two terms won't necessarily cancel, but they'll get close to it. I will say. Your entropy change will be dominated by this part, okay? And it'll only be a small correction from kind of these things. All right. And then what would I use for delta S of the surroundings? in general, the entropy change of the surroundings is equal to what? Negative Q over temperature of the surroundings, right? Which in this case is going to be N delta H fusion divided by temperature of the surroundings, right? Which is minus 20 degrees Celsius. Obviously, convert that to Kelvin, but yeah. So N delta H fusion. Okay. And then delta G. How would I get delta G? At minus T delta S, right? And delta A. Delta U minus T delta S, right? Which the fact that delta H and delta U are basically the same thing, you get delta G, delta A are almost the exact same thing. So questions about this example? All right. Should be kind of the same type of stuff here. Actually, I think I left off the one entropy change, and I look about this, right? Here I did technically leave off that, you know, you could use the other entropy change. All right, so the entropy again, like the entropy itself isn't equal to this or to this. Oh, I put S fusion here, right? This would be delta H fusion over T. I mean, you're typically not given what the entropy change is for that reaction. So really, should just be delta H. All right, so yeah. But technically, if you're given the entropy of fusion, right, the entropy change for that fusion reaction, right, for going from a solid to a liquid, you could use that entropy change multiplied by the total number of moles to get the total entropy change, right? Just often not given that, right? But all right. So yeah, so I mean, there's other examples here. They're posted again on Canvas already in the supplemental notes. If you're interested in them, again, as just things to review and go over. For those who are here in class, I have homework 3 graded. If you'd like to pick it up, you're welcome to do so. Okay. Scores have also been uploaded online on Canvas. You can always check out your scores online. So, any questions from those here on Zoom before I close out the session? Doesn't seem like it, so I will see you guys on Wednesday.